Hello, this is my lecture about compound semiconductors. So compound semiconductors are mixture of elemental semiconductors. So if you use just one element like silicon or germanium, like silicon is mostly used for electronic devices. Germanium was used in early days of semiconductor devices, but now we use many different combinations of semiconductor materials and we use them in compounds. So if this is an example of a unit cell of a diamond lattice structure. In case of a compound, what will happen is, for example, if it's a binary compound, then one site will be for group 3 element, if it's a 3, 5, the next site would be for a group 5. So 3, 5 elements will rotate in this diamond structure. That's in that case it's called zinc blende. But if there were uh, more than two uh, two elements from group 3, then group 3 sites will rotate between those two atoms in this structure. So for example, if we were to identify uh, red ones with uh, one element from one group, and we say the green one is the element atoms from the other element from group 5, for example. So if I would mark these greens, and then there will be, of course, one green somewhere here, one green will be here, then 3 and 5 will rotate, and so on and so forth. Now, if there is, for example, from group 3, we have two of those ternary compound, then the site, which is being shown here for red, will be alternated by those two atoms, those two types of atoms. So hence the compound have their own order of things where they will be using the same structure, but the placement would be as such that one group will be connected to 4 atoms from group other group. So 3 goes with 5, 2 goes with 6. Now, these compound semiconductors like gallium arsenide, they have a mixture of bondings. They may have both ionic and covalent bonding forces in their structure. And this would be basically result into their different placement in the periodic table. Now, the compound are essentially used for very specialized uses. For example, when we are talking about optical materials. So here it says that it's either used for uh, high-speed devices or devices that deal with light. So essentially, if we talk about using them for optical application, then we have to know that we can tweak their band gap and we can tweak the wavelengths that they can accept or emit. And when we talk about the tweaking of wavelengths, which means that with a very small change in the fraction of those elements, we can have a large variation in their optical and electrical properties. It will also result in big change in their mechanical and chemical properties as well. Now, for any combination, for example, binary material, gallium arsenide, they have a very specific band gap and hence wavelength. So for gallium arsenide, that falls in the near infrared region. Similarly, gallium phosphide have a specific band gap, which is 2.3 electron volt, and its wavelength then corresponds to green portion of the spectrum. Now, this has a very simple extension to quaternary compounds as well, where if we talk about 3 and 5, then two elements would come from three, two elements would come from four, sorry, from five, and in combination, they all will result into fulfilling the uh, structure of a zinc blend if they belong to zinc blend structure. So this gives us a very wide variety of materials. And if you think about LEDs that we use, which give different light, they are built from variations of materials and then which will correspond to those specific wavelengths that they emit, or in terms of other optical devices that would be detectors. Again, the detection frequency can be very precisely adjusted with that.